Hello everyone, welcome to our channel Mathematics Pathshala. This is a problem of CSIR NET September 2022 Mathematical Sciences. The question ID is 317. Let's see the problem. This is a problem of abstract algebra. Let R be a commutative ring with identity. Let S be a multiplicatively closed set such that 0 does not belong to S. Let I be an ideal which is maximal with respect to the condition that S intersection I equal to phi, then which of the following is necessarily true? Option 1 says that I is a maximal ideal. Option 2, I is a prime ideal. Option 3, I equal to singleton 1, and option 4, I equal to singleton 0. Let us now uh, see the examples that which options cannot be true. So for this, first if we take the ring R equal to Z plus dot with usual addition and usual multiplication plus and dot denotes, and if we take S equal to Z minus singleton 0 here, then clearly S will be a multiplicatively closed set and 0 does not belong to S. Here if we take I equal to singleton 0, then see the given condition satisfied because I is a maximal ideal with respect to this condition S intersection I equal to phi. Now see here I not equal to singleton 1, so our option 4 is not true in general, and also here I is not in general maximal ideal because there is an ideal 2z which probably contains I and not equal to R. So I is not maximal ideal in general. So for this example, option 1 and option uh, 4 are not correct. It is done from this example. Now let's see if we take another example, say the ring, we are taking same ring R equal to Z plus dot, and we are taking S equal to this type of elements a 7 to the power n, where n belongs to Z and n greater than equal to 0, suitable non-negative integers, all such n. So clearly S is a multiplicatively closed set in this case, and if we take I equal to 2Z and also 0 does not belong to S, and here if we take I equal to 2Z, then see that this condition that S intersection I equal to phi is satisfied, and since I is the maximal ideal in Z in general, so I is a maximal ideal satisfying this condition. So now see I equal to singleton 0 is not true in general because such I exist which is not equal to singleton 0. So option uh, sorry, in our previous example we have shown that option 1 and option 3 are not true in general, that I not equal to singleton 1 is there. So sorry, from our previous example we have shown that option 1 and option 3 are not true in general, and from this example since I not equal to singleton 0 we have shown that option 4 is not true in general. So there is left only one option and it will be also true. We now prove this result. In this case, I will be a prime ideal. So for this, if we take any two elements A, B, so to prove this result, this we have taken arbitrary the R be a commutative ring with identity, any ring, and S be a multiplicatively closed set such that 0 does not belong to S, and I is an ideal such that maximal ideal satisfying this condition S intersection I equal to phi. These are all given for general any ring R, any commutative ring R with identity. Now we have to prove that I is maximal, I is a prime ideal in this case. So now take any two element A B belongs to R such that A dot B belongs to I. We will show that A belongs to I or B belongs to I. So for this, if possible, we let A, B both does not belong to I. A does not belong to I and B does not belong to I. Now this ideal containing I and this A, since I is a maximal ideal satisfying this condition that A's intersection I equal to phi, so this ideal, and since A does not belong to I, so this ideal should be either equal to R, or this ideal, the intersection of this ideal with S is not equal to phi. Since I is the maximal ideal with respect to this condition, so this will happen. Similarly, since B does not belong to I, so this is the ideal which properly contains I. So this ideal is either equal to R, or this intersection should be non-empty. If I is only maximal ideal, then this should be R and this should be R. But since here satisfying some condition, so this also should happen. So now, if first we suppose that this condition hold, that I A, this ideal containing this I and A is equal to R, then see, 1 belongs to R, so 1 belongs to this I ideal generated by I and A, so 1 can be written as 1 equal to x plus RA, where this x belongs to I and R is any element of R. So now B equal to B into 1, so it will be Bx plus RAB. So since this we can write this in this form xb, same thing because R is commutative xb. So as x belongs to I and I is ideal, so this will belong to I, and also this AB belongs to I, so RAB belongs to I, so B belongs to I, which is a contradiction as we have supposed that B does not belong to I. So this thing cannot be true, that IA equal to the ideal generated by I and A equal to R. So exactly in similar manner, this case, the ideal generated by I and B is not equal to R. So these two conditions will not happen. So what will be left to be happened? We must have this and this, because this is not so and also this is not so. So for this we must have the ideal generated by this I and A intersection is not equal to phi, as well as the ideal generated by this I and B intersection is not equal to phi. So take one element S1 belongs to this set and take one element S2 belongs to this set. So now this S1 is of the form this x plus say R1A, and S2 is of the form say y plus R2B. Now this calculate S1 S2, which is equal to x plus R1A dot x plus y plus R2B, and after this multiplication we have xy plus x R2B plus y R1A plus R1 R2 AB. Now see here, this x and y both from I, so xy belongs to I, x belongs to I, so R2B, x R2B belongs to I, y belongs to I, so y R1A belongs to I, AB belongs to I, so R1 R2B belongs to I, so both are from I and the sum will also belong to I. Also we are given that S is a multiplicatively closed set, and also S1 S2 both are in S. So their multiplication also S1 S2 belongs to S. So now S1 S2 belongs to I as well as belongs to S. So what we have, S1 S2 belongs to S intersection I, and which is non-empty, but which is also our contradiction, that I is maximal ideal. Satisfying this condition, that S intersection I equal to phi. So for all such cases, we have we have we have come to a position that we get a contradiction. So for this we must have, so why this contradiction came, because we have supposed that AB belongs to I with A does not belong to I and B does not belong to I. So this cannot happen. So we must have AB belongs to I implies either A belongs to I or B belongs to I. So I is a prime ideal. So now we have option 2 is the correct option. So option 2 is the correct option. So this is the solution of this problem.